The addition law of probability is the probability that either event A or event B is going to occur. There's two formulas for the addition law of probability. One is if there's no chance that both event A and event B can occur at the same time, and the other is if there is some chance that both A and B can occur at the same time. So the one, if A and B cannot occur at the same time, so let's say, let's think of a good example. You cannot be in two places at once. So the probability of being in Philadelphia and the probability of being in Dallas, Texas on January 2nd in the year 2020, they are completely separate from one another. You cannot be in both of those places at the same time. This would be an example of when you would use this first formula, the probability of A, then that U symbol, B, the probability of B. Then that would be equal to finding the probability of A plus the probability of event B. So in this case, they're mutually exclusive events. That's when you use this first formula, if you can't have both of those events happening at the same time, or the outcomes at the same time. Another example you might think of is cancer status. You can't both have cancer and not have cancer at the same time. You either have it or you don't. So that's an example of that. For the second formula, if there is some chance that both A and B, the events, can occur at the same time, then we want to use this formula, which is the probability of A plus the probability of B minus the probability of both A and B occurring at the same time. So the probability of both A and B looks like written out A with an upside down U, then the B event. On the next slide are some examples which will help clarify what this means and what it looks like in an actual calculation. So the first example, pet ownership in a household. So what is the probability in some sample we have, of owning a cat or owning a dog? So in this case, which formula do we think we should use? Well, first, let's look at the probabilities that were given. So the probability of owning a cat was 0.35. The probability of owning a dog was 0.30. And the probability of owning both a dog and a cat was 0.15. So since the question includes or, we want to use the addition law of probability. And then the next step would be asking ourselves, can these two events happen at the same time? Well, yes, you can own both a cat and a dog at the same time. So we want to use that second formula from the previous slide. The third step then is actually filling in this formula. So the probability of a cat was 0.35 plus the probability of owning a dog, which was 0.30, minus the probability of owning both a cat and a dog, was 0.15. So this comes out to a 50% probability of someone owning a cat or a dog. The second example is based on clinical data from 2010. What's the probability of someone being diagnosed with stage 1 or stage 4 of cervical cancer? So here, we want to first look at the question, and it includes the word or, so that's how we know we're going to use this addition law of probability. Then we want to look at the second part. Can the two events occur at the same time? So can you be diagnosed at stage 1 and stage 4 of cervical cancer at the same time? No, you would either have stage 1 or stage 4. So now we want to use that first formula from the previous slide. The next step is inputting those values that we were given in this scenario. So the probability of having stage 1 was 0.3, Probability of stage 2 was 0.3, probability of stage 3 was 0.2, and the probability of stage 4 was 0.2. So what we want to use in this step 3 is the probability of having stage 1 plus the probability of having stage 4. So in this case, the probability of stage 1, 0.3, plus the probability of having stage 4, 0.2. When we add those together, we get 0.50, which equates to a 50% chance or probability of someone being diagnosed with stage 1 or stage 4 cervical cancer. This is another example using the addition law of probability, where we get into a little bit more thinking. So this is an example using Titanic passengers. So there's men, women, boys, girls, and then the total is listed on the far right of the table. Then we have 2 rows that divide by those that survived the Titanic and those that died. And then at the very bottom is the totals for each of the columns of men, women, boys, and girls. So if we wanted to find the probability of getting someone who is a woman or a child, we first want to ask ourselves, which formula are we going to use? So can these events occur at the same time? Can you be a woman or a child? No. So then which formula should we use? The top formula or the bottom one? Since they're mutually exclusive, we would want to use that top formula. So the probability of being a woman or plus the probability of being a child would be 318 out of 2,223, the total sample, plus the number of children. So we would have to add this up, 64 plus 45, so 64 plus 45 divided by the total sample of 2223. The next example is finding the probability of getting a man or someone who survived the sinking of the Titanic. So we want to look to see if these events can occur at the same time. Can they? Yes, these events can occur at the same time because you can be a man who did survive the crash or the sinking. So now we want to use that bottom formula since you can be in both of those categories. So to find the probability of being a man in this sample, you would want to use the total number of men, 1692, divided by the total number in our sample, 2223, plus the number of survived. So that we're going to go to the total number of people that survived, which was 706, and divide that by 2223. Then we're going to subtract the probability of being a man and surviving in this total sample. So that would be going and finding the intersection of where survival status and men in our table meet. So let me try and draw on here. So if we look down men and survival, we get to this first part with 332. So that would be the number of men divided by 2223 that we would want to use. So let me write this example out a little. So 1692 divided by the total sample, 2223, plus the total number survived, so 706 divided by 2223, and I know this is really sloppy, I'm sorry everyone. Then we're going to subtract that from that 332 divided by 2,223, and that would be the probability of getting a man or someone who survived the sinking. So this is for this second question, the red writing at the bottom. Let me clear this off. So now we want to look at the probability of getting a woman or someone who did not survive. So here we want to look again at can these events occur at the same time? Yes, you could be a woman in this sample and you could have survived, or you could have not survived, rather. So again, we want to use that bottom formula. So what are we going to use? What values are we going to use? So to find the probability of being a woman in the sample, we would have 422 divided by the total sample size, 2, 2, 2, 3. Then we would add to that the probability of being having died in the Titanic sinking. So that would be found going from died over to the total column, and that would be 15, 17. So 1, 5, 1, 7 divided by the total sample, 2, 2, 2, 3. Then from that, we'll subtract the probability of being a woman who died. So that would be 104 divided by the total sample again. Woo! This math is going a little crazy here. Sorry. So when you would compute that with a calculator, you would get the answer of the probability of being a woman or someone who died if we randomly selected one person out of this sample.